Okay, there are two examples that we did not get to that I wanted to look at. We looked at 6 examples in class. Now let's look at 2 examples that bring up exceptions to the octet that we've been focused on up to this point. So the first of these 2 is this beryllium dihydride molecule. So let's start off the same way. Let's go ahead and get our total. We've got 2 electrons from beryllium and 1 from each of the hydrogens for a total of 4. We'll go ahead and join them with single bonds, and we get a structure that looks like this. So we've used 4 valence electrons in forming those bonds. There are no valence electrons left over. But we look at beryllium, and we notice that beryllium only has 4. So normally, we would then go ahead and start over again and try to get beryllium an octet by doing some sort of multiple bonds, doubles or triples or whatever it would take. But I'm going to stop you. You don't do that. This is one of the situations where we have an element that can actually possess what's called an incomplete octet. It can have less than 8 valence electrons and produce a valid structure. And that's what you see here. There are only a handful of elements that are in this position where we generate a legitimate dot structure for this molecule. There are actually 3 elements that this holds true for. When you run into these and you end up with less than 8 valence electrons, it's okay. Don't try to do double and triple bonds. The 3 elements are beryllium, boron, and aluminum. Now, that doesn't mean they'll always have an incomplete octet, but many times they will. And when you run into that situation, it's okay. And you've got a valid dot structure for the molecule. All right, that's called an incomplete octet. Only 3 elements fit that criteria. Now, let's move on to a second example that also produces a situation we haven't seen before. So here's our compound with sulfur and astatine in it. Again, let's get our total number of valence electrons, 6 from the sulfur, 7 from each of the astatines for a total of 48. We should be getting pretty practiced at this. Let's go ahead and draw in our 6 bonds with the astatines. Obviously, 2 electrons each. That's going to be 12 valence electrons used up, leaving 36 left over. We can quickly see that each astatine needs 6 more, so that takes up the remaining 36 valence electrons. I've used up all of the available valence electrons. There are none left. But I notice something unusual. I look at my central atom, sulfur, and I notice that it has actually 12 valence electrons. We haven't encountered anything like this before. This is what is known as an expanded octet. There are elements that have the ability to accommodate more than 8 valence electrons, and in some situations they will have more than 8 valence electrons. The only way this can happen is you have to have a valence shell that can hold more electrons. If you remember a while back when we talked about the shells or the energy levels, we said that the first shell could hold up to 2 electrons, the second shell could hold up to 8, but when we get to the third shell, it can hold up to 18. And as we progress further out and get a bigger and bigger diameter shell, they can accommodate more and more electrons. So the only time you're going to see an expanded octet is if the element that's in this situation occupies a period. Remember, the periods correspond to the valence shells. You'd have to have a period, an element in a period that is the third or higher, the third row or the third period or higher. Those would correspond to larger valence shells. So if an element is in the third row on your periodic table or higher, that means into the 4th, 5th, or 6th row, they can have an expanded octet. They don't have to have an expanded octet, but if you run into a situation where this takes place, again, it's okay. That would be a valid structure. So if you look up sulfur on your periodic table, in fact, it is in the third row, which is the third period. That means its valence electrons are in the third shell. And as I said, the third shell can accommodate up to 18 valence electrons. In this particular case, in this particular molecule, it has 12 in the valence shell, and it's okay. It has an expanded octet. Now, in another problem, it may not have that. You don't have to, it's not something you force. We saw that with the sulfate ion that we looked at in class, where it had an octet. Sulfur had an octet in that example. So it's not required, it's just a possibility.